Okay? So the first part of the lecture today, I will continue presenting few topics. So it will be theoretical material. And then in the second part, we'll do a practical exercise using a tutorial that I will guide you through. So we concluded the previous lecture defining the concept of conjugation in radial quantization. And we discover using the cylinder picture that our conjugation basically amounts to perform an inversion. So if you have an operator O, which is inserted at some coordinate x, if you take the complex conjugation in radial quantization, this corresponds to perform an inversion. And performing an inversion means that you have to take the operator inserted at x mu divided by x squared. And in addition to this, there is also a prefactor, which comes from the basically the conformal transformation that you have made. So this prefactor is x to the minus 2 delta O. Okay. So this is how operators transform under conjugation in radial quantization. And using this definition, now we can define what are conjugate states. So a conjugate state, in particular, for instance, if you take a conjugate state represented by the action of an operator OX on the vacuum, if I take the complex conjugate of this state, this becomes x to the minus 2 delta, and then the conjugate, the cat instead of the bra, O of x over x squared. Okay, so this is the conjugate of an operator inserted at x, and now we can take the limit x going to 0 to properly defining primary state, because this object here is a combination of a primary state and descendant. So you want to define what is the actual primary state. So I can just take the limit x going to 0 of this expression and define a state, a pure state, if you will, a primary state conjugate as the limit. I want to send x to 0. Let me redefine this quantity and call it y. Y mu is going to be x mu divided by x squared. So when x goes to 0, y mu goes to infinity. Okay, and then I just get y to the 2 delta O of y. Okay, so this will you can define the conjugate state as a limit of a vector, an operator acting on the vacuum on the left, and then rescaled by this quantity here. This will be my conjugate state. And now, using this definition, we can, for instance, compute the two-point function and relate them to norms of states. For instance, let's start from the 2-point function of scalars. Here, this is going to be x1 O of x2. Okay, so let me write this in the following form. The vacuum, some operator conjugate, which will be x1 to the minus delta O, sorry, 2 delta O. Operator inserted at y1 conjugate, where again y is related to x with this definition, and then OX vacuum. Okay. This is the same definition as before, just test the inequality. And then I can use the translation operator to set to 0 both these arguments, but I have to pay the price of the exponential. So this will be x1 to the minus 2 delta O. Sorry, let's go here. X1 to the minus 2 delta O. Then I have the vacuum. I have e to the y1 p O of 0, e to the minus y1 of p conjugate, and similarly for x, for the other operator, e to the x2 p O of 0, e to the minus x2 p, and then the vacuum. Okay. And now we can take the conjugate, and we can remember that the conjugate of the generator P is actually K. And so this becomes something like x1 to the minus 2 delta O. Of course, when a generator acts on the vacuum, it simply gives you when P acts on the vacuum is invariant, so it's not a problem. And also, when K acts on the vacuum on the left, it's also invariant, because it's just a conjugate of this, right? If you take the conjugate of this, you get something like e to the minus xk. So what I'm going to get here is the vacuum, the operator inserted at 0, e to the y1 k, e to the x2 p, and then O of 0, and then the vacuum again. And again, I use the fact that the conjugate, here you have to flip, and the conjugate of P is K, as we said this morning. And so we can use the definition of before and write this quantity here as sorry, here there's well, in principle there should be a dagger, but let's take O Hermitian when inserted at 0. And so this becomes x1 to the minus 2 delta, the state O on both sides, and then in the middle you have this operator e to the y1 k e to the x2 p. So this is very interesting because now we can expand this object in the exponential. We can make an expansion in x1 and in y1 and x2, and relate and find a whole series of terms. So this would be something like x1 to the minus 2 delta. There is the norm of the primary, and then you get the second term is something like let's see, it's going to be y1 mu x2 nu divided by y square sorry it would be y1, but if I write in terms of x1, this will be x1 mu x2 nu divided by x1 square. Okay, this is what y1 was. And then you have the operator O, sandwich. You have sandwiching in the first order expansion there, which is simply k mu commutator with, sorry, not commutator, with p nu. Plus dot 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 dot. This is the first order. Eventually you have all of them. And the nice thing in this expansion is that now you can use the algebra of generators to compute all this. So for instance, let's see one of them. The expectation value of k mu p nu between the two, the operator O, and let's assume that O is a scalar, just for simplicity. Okay, and it's a primary, of course, which means that if you revert the order of k and p, you would have k acting on the right on a primary, which gives you 0. So you can substitute this object with a commutator. With no harm. And now you can use the algebra. So you can remember that the commutator of k mu p nu is 2 delta delta mu nu, or eta mu nu, minus 2 the generator of rotation, but generator of rotation acting on a scalar primary, it's trivial, it gives me 0. So this I can forget about this object, and so I just get eta mu nu contracts with the two x's, and I just get 2 delta okay, so you can just plug in here and you get a very nice expression for the second order. So this is just 2 delta eta mu nu O. Okay. So and this dot dot dot, you can go on, you can perform this trick as many times as you want. So this was an example of how to use this. Interestingly enough, if you compare this expression and the subsequent terms with the expansion of the two-point function, because this two-point function we know exactly, right? This two-point function we know exactly, and if you look at this at the expression that we got, we have a leading term. So we can normalize to 1, for instance. So we have a leading term, which corresponds to, where should I write this? That's right here. You can compare with the usual expression of the 2-point function, which is 1 over x12 the power 2 delta. Here delta was always delta O. Okay, I forgot to put labels somewhere, but it's always the same. So if you expand this object around in small x2s, okay, around x2 equal to 0, you get the first term, which is exactly this one, plus subsequent terms, and nicely enough, you would see that all term matches. Okay, so there's another way to compute this 2-point function using the norm of the states. And now I would like to use again this argument to prove a very powerful statement about a CFT. And this is a statement that I anticipated some time ago, and it's basically exploring consequences of having a unitary theory. So in unitary theories, you would like to have norms of operators to be positive. This is if you are in a Lorentzian theory. If you are in an Euclidean theory, having norm of states is not really a requirement, but there is a condition under which if you have an Euclidean theory, if you assume that a certain condition which is called reflection positivity which I'll explain in a second. If this condition holds in an Euclidean quantum field theory, then there are theorems that allows you to, well, basically tells you that if you continue this theory to a Minkowski theory, then you would end up with a unitary theory. So this is a request that you would like to have in your theory. And this reflection positivity simply tells you that norm of state defined in our way must be positive. Okay, so if you take a state here, this has to be positive, where this state is literally the conjugate as we defined this morning. Okay, it's the conjugate according to your quantization condition. Okay, so let's check how this works in our example. And the reason you might see that something interesting is going on already comes from this argument here. Because if, for instance, suppose that we started from a primary O such that the norm of O is positive. Okay, so O we define it to be 1, which you can always do provided you scale O. And now you can ask the following question. Now that I fixed the normalization of the primary operator, is it guaranteed that that all the other states that are in the same irreducible representation, namely all the descendants, also have a positive norm? In particular, if I take a first descendant, let's call it P mu, or even simpler example, P0 of the state acting on the state O, and I compute this norm. Okay, this is defined according to, it's basically this object where you set mu and nu equal to 0. okay? And if O is a scalar, we can use the same argument as before. And this is simply 2 delta times the norm of the primary. So if we choose the norm of the primary positive, you better have positive dimensions. Otherwise, you would end up with a descendant which has negative norm, which is not something that you want. So in 2 lines, we already obtain a very powerful constraint on the type of irreducible representation that you can have in a theory which is reflection positive. So for scalars, delta has to be larger than 0. Okay? And now I would like to do the same logic. I would like to repeat the same logic, but for generic operators. So there is some group theory involved, but it's not a big deal. And interestingly enough, it's just a generalization of this argument. So all the constraints come from inspecting the norm of the first descendant, except for scalars where you have to inspect the norm of second descendant. And that I will not do. I'll leave it as an exercise. Okay. So let's see how this goes. Let's consider an operator O, generic operator O, which has index, let me call it capital I, some spin index. Okay, it belongs to some representation of the Lorentz group, or the rotations, since we are in Euclidean, and it has dimension delta and let's say some spin. Let me call it R, little r, the irreducible representation of rotation. And so I want to consider the norm of this object. In fact, I want to be a little bit more generic. I want to consider the inner product of this. P nu O j sorry, I forgot x here. Let's be precise. First of all, let me define what I mean by the 2-point function. So OI, OJ is going to be delta IJ. Okay, so only operators with the same spin, with the same index, have non-zero 2-point function. And then I want to consider the following object: P nu OI dagger times P nu OJ. Okay, so this is basically a scalar product, but it's written in this form. So what is this? This is, as before, is just OI, K mu, P nu, OJ. So I'm just repeating the same step as before. But now, because we have some non-trivial irreducible representation of the rotation, the commutator of this object, is primary again. The commutator of k with p does not only contain the term proportional to dilatation, to the dimension basically, but also a term proportional to the generator of rotation. So this will be, when I take the commutation relation, this will be 2 delta and then delta mu nu minus twice the generator in the appropriate representation. Okay, let me call it R, capital R, of mu nu. And this object here as right. Well, to be more precise, let me be even more precise. Okay, let me write everything. This will be OI to delta eta mu nu delta I j minus 2. So here you have the generator in the reducible representation, and it's contracted with indices ij. Okay, so it's the appropriate representation with indices ij. Okay, and then you would like this object here to have positive norm, which means that this matrix in the ij space, and the matrix in the ij space, has to be semi-definite positive in order for this scalar product, for this matrix product to be positive. So the condition here, slightly more involved than before, is just that delta has to be larger than the maximal eigenvalue of this metric. Of R. Okay, so let's try to make this this condition a little bit more quantitative, and to do that we have to compute what is the maximal eigenvalue of this quantity here. Okay, so to do this, let me write the representation of this generator, mu nu, index ij, in the following form. This you can write as 1/2 LAB, which are the generator in the fundamental representation, index mu nu, times some metric S A B I J. So let me define this quantity here. This is simply LAB index mu nu is delta A mu delta B nu minus delta A nu delta B mu. Okay, these are, you might recognize the generator of rotation in the fundamental representation, in the proper representation, which is the fundamental. Okay. Okay. And so the point is the following. Let me write L AB as AB. Okay, forget about the other indices. This is a sum over all the indices of the generators, and there is a nice relation that allows you to express this as squares, as Casimir operators, if you want. And I'm sure you have seen this trick many times in quantum mechanics. So you can write LA. This is basically sort of L. Let's call it. You can collectively call this object alpha. Alpha S alpha. So it's a scalar product between these two quantities. So you can write as the square, but then you have to subtract L square and also S square. Okay. This is in quantum mechanics, you do this trick all the times. For instance, when you have spin orbit interaction, you can write like this. But now you can see that these objects here are the square of the generator. So these are basically Casimir operators. And Casimir operator, they have definite eigenvalues. So in particular, for instance, let's see. So I can write this as 1/2. Actually, the Casimir is minus L square in my convention. So you can write the following object as the Casimir of the vector representation, let me call it V1, plus the Casimir of the representation little r, little r. And then you should subtract the Casimir of whatever representation you get here, which is basically little r times V1. Okay. This is a product of representations. Generically, this might contain more than one representation. And so now we can answer the question using this trick. For instance, the Casimir of V1 is going to be, well, generically the Casimir for a representation where little r is traceless symmetric can be written in a very simple form. Or suppose little r is traceless symmetric representation, traceless symmetric with L indices, then the Casimir of R, particularly V1 is such a representation with L equal 1. So then Casimir L has a very simple form of which is L plus D minus 2. Okay, it's a constant because it's a Casimir operator, commutes with everything, so it has to be proportional to a constant. And so now we can write, we can use this fact to compute what is the maximal eigenvalue of this object. So delta has to be larger than 1/2 so what is the Casimir of L plus the Casimir of L equal 1, which is the vector representation, minus the Casimir of this tensor product. So VL times V1. So the strongest bound comes from the case in which this is minimal. Okay, so you have to inspect what is this tensor representation, and you have to take the one with the smaller Casimir, so that when you subtract, you get the strongest bound. And this comes, and if you remember, you have a simple composition of reducible representation for SOD. V1 tensor product with VL contains several things, among which contains VL minus 1, direct sum with other stuff, which always have larger Casimir. So this is the one that we are going to be interested into, because it has the smaller Casimir. So if I use this, I obtain a very simple relation, which is delta has to be larger than L, just plugging in all this formula here for different values of L, L plus D minus 2. Okay. So this is a very powerful result. It tells us that not only delta has to be larger than 0 for scalars, for non-scalar, it has to be larger than this value, which depends on L. So the larger is the spin, the larger the dimension of the primary operator has to be in order not to have negative norm states as descendant. Okay. For the case L equals 0, this does not really apply, because if you compose V1 with V0, you don't get V minus 1, you only get V1. So for scalars, this reasoning does not apply. You don't get any such. You don't get a constraint like this, but you have to go to the second descendant. I'm not doing that, but you can do yourself. You can compute the norm of the second descendant of a scalar and show that the request that the norm, for instance, of p mu acting on scalar phi with dimension delta larger than 0 implies for the scalar that delta has to be larger than d minus 2 over 2, which incidentally is the dimension of free scalars in d dimension. So free theory is consistent. So to to collect our results, we have that for scalars, we have this condition that the dimension of the primary state has to be larger than this value, and then for traceless symmetric tensors with spin L, you get the delta has to be larger than L plus D minus 2. There is one exception, which is delta equals 0, which I didn't delta equals 0, L equals 0, which is the identity operator. This is still consistent. All these these conditions here are called unitarity bounds. And are the conditions in order to have not to have descendants in your irreducible representation which have a negative norm or zero norm. When one of these equality is fulfilled, so it's saturated, then one of the descendants has exactly zero norm. What does this mean? Let's see an example. Consider, for instance, a spin 1 operator. Let me call it J mu. Okay. And according to this formula, delta J has to be larger than D minus 1. And when delta is actually, when delta J is equal to D minus 1, what it means, according to our discussion, is that the norm of P mu J is 0. Okay, so this is a null state, and sorry, yeah, you have to. If you remember, the descendant that vanishes is one with L minus 1 spin. So you have to contract these to get the L minus 1 representation. So this is the one that vanishes. And if you inspect this condition, this is equivalent to say that the mu J mu is 0 as a quantum statement. Okay. So when these unitarity bounds are saturated, you have a conserved operator. And in conformal field theory, conserved operator means that some of the descendants have not, zero norm, which means that the representation is shorter. Okay, you have some operator missing in the representation. You have a shortening of the multiplet. When the operator instead, when the dimension instead is strictly larger, then the representation is not short, it's long, and all the states have positive norm. None of them has zero or negative norm. You can do the same trick for spin 2. Okay, spin 2, when delta t is exactly d, it means that the operator is conserved. It means that one descendant vanishes, and this descendant is exactly the mu t mu nu. Okay, this has zero norm. So again, the operator is conserved. Okay. Any questions about this? No questions. Okay. In the last, let's say, 10 minutes, I would like to start discussing a different topic, which is the operator product expansion. Also called E. So the operator product expansion is a simple consequence of our interpretation of the theory as radially quantized. So operator inserted on sphere at some point create states on the boundary of a sphere surrounding them. So if you have an operator O1 inserted at some point, you can draw a sphere, and as we said, this generate a state on the sphere. Okay, suppose this is inserted at 0. Now, what happens? And the state here, if there is such an operator, is a primary. If the operator is inserted at some x, this state is a superposition of primary and descendants, but still is an object that belongs to a well-defined irreducible representation of the conformal symmetry. What happens now if you have two operators? Let's say a O1 inserted at x1 and some O2 inserted at x2. Okay. In this case, by the same logic, I can still define a state on the boundary of a sphere surrounding the two operators. We call it O. Let me call it psi. This is a state, but for no reason I don't have to expect that this is in some irreducible representation of the conformal symmetry. And indeed, it will not. On the other hand, I can, because I have a full Hilbert space of states living on the sphere, I can decompose in a complete basis. Okay, so I can write this as a sum of let's say delta and spins of operators of state of the form O delta L. Okay. I can always, and there will be some coefficient here. C delta L. Okay, so because I can always this is clear, this is quite intuitive, and now I can do the same procedure inside any correlation function. Okay, if I have a correlation function involving multiple operators, I can always, so suppose I have several operators here, I can always take two of them, draw a sphere that surrounds two of them, and replace the state living on the sphere with a sum of irreducible of states in a well-defined reducible representation. And because we have an operator state correspondence, each such state can be associated to an operator living at the center. So effectively, I can replace any two operators in a correlation function by an infinite sum of operators. Okay, so you have to think this in terms of the following statement will be valid in any correlation function. Of course, it will not be valid as an identity, but you can think that whenever you have two operators, O1 and O2, inside the correlation function, you can replace this as a sum of some coefficient I1 to k, sum over k, operators k, operator k, inserted, for instance, at some point inside the sphere. I can choose, for instance, to quantize around x2. Okay, I can take a sphere which is centered around x2. This is just a choice. Okay. And then this coefficient here must encode, first of all, the dependence on x12, which is the radius. And also, of course, I don't expect to have only a sum over primaries, but I also expect to have descendants. So generically, this can depend also on derivatives. Well, let's literally use derivatives with respect to the point 2. Okay. So this statement here, which is, again, I stress, is valid inside correlation function. It's called the operator product expansion. Not only is valid all inside correlation function, but you have to make sure that there is no other operator living inside the sphere. Okay, so this statement does not hold if, let's say you have three states. Okay, O1, O2, O3, inserted like this. Okay, the operator product expansion does not hold, for instance, in this sphere. You cannot replace O1 and O2 with this expansion because there is O3 closer to O1 than O2. Okay, so on this the state defined on this sphere also contains a superposition of things coming from O3. The only place where the operator product expansion would be valid would be, for instance, on a sphere like that, or on spheres like that. But you cannot expand. You cannot replace O1 or O2. You can only replace things that are closer than any other operator. Okay. Is this clear? And another thing that should be noticed is that here I decided to replace this state as an expansion of in primaries center at x2, but in principle it's just a choice because I can center my sphere wherever I want as long as it contains the two operators. So this can be written also as a function, as a sum over k, some other coefficient, twiddle, I to k, 1 to k, x12, oops, sorry, x1, 3, x23, d3, operator k, center inserted at x3. With x3, arbitrary. Okay, this is still possible. This is not very convenient, but it's just to point. I want to point out that the choice of where to insert the operator is just a convention. Okay. So this is a very powerful statement. Let's make some use of it. And in particular, let's see, what do I want to show? Okay. So let's make some use of it. It's so powerful because it allows us to compute correlation function in terms of smaller correlation function. So let's say you have three scalar operators, O1 of x1, O2 of x2, O3 of x3, inserted in such a way that x1 and x2 are closer than x3, for instance. And then you can use the operator product expansion, which is usually denoted like this, to write this quantity as a sum over k. Let's say C12k x12 of OK, x2 O3. Right? But then this object here, we know that this is a two-point function, and two-point functions are diagonal in the space of operators. So this term will be non-zero only when OK coincides with O3. And so this infinite sum actually reduces to a single term. So it C1, 2, 3, x1, 2, d2, O3 of x2, O3 of x3. Okay? But in turn, we can use this nice property to define what C123 is, or to extract what C123 is, because we know exactly what is this three-point function. This three-point function looks like something like some coefficient f123 divided by a known function of coordinates x12 delta 1 plus delta 2 minus delta 3 x13 delta 1 plus delta 3 minus delta 2 and x23 delta 2 plus delta 3 minus delta 1. Okay, so you can take this equation here as a definition, or if you want a consistency condition that this differential operator here has to obey, and you can simply expand, for instance, the function on the left and match it with derivatives of, so this is going to be x23 to the power 2 delta 3. Okay. So you can expand this term around for x23 much larger than the other two distances, and you can read off each term in this expansion. For instance, you can show, I leave you as an exercise. So the exact form of this C123 differential operator is not really important. It's convenient to know that it exists and can be computed, but it's never actually used in any computation. So let me just write once and for all. So this 1, 2, 3, which is a function of some coordinate and derivatives, is going to be proportional to the three-point function coefficient f1 to 3. Okay. X to the power, this is in a specific example in which delta 1 equal delta 2 equal delta, and delta 3 equal, let's say delta, well, delta 3 is, it's arbitrary, okay? So this is going to be delta 3 minus 2 delta 1 plus 1/2 x dot derivative plus, say, alpha x mu x nu the new, plus dot, 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 dot. Okay? It has an infinite expansion in x, and this coefficient alpha can be computed, for instance, and in this specific example, it looks like delta 3 plus 2 divided by 8 delta 3 plus 1. Okay, so this is an exercise you can check. Just by doing the expansion and matching derivatives from one side and the other, from both sides. Okay. I'll stop here, and I'll continue tomorrow expanding a little bit on this operator product expansion and going ahead with conformal blocks. Questions? Okay. Sorry? No, there will be the tutorial, practical tutorial now. All right. So the idea of this hour and a few more hours in the following days is to give you a practical introduction to numerical techniques that will be useful later on. So for today, I'm just going to present a very simple problem that can be addressed in several ways, and we will use a software that has been developed particularly for this kind of problems, which is called SDPB. So I invite you to go on the latest website and download this file here. Should be a zip file which contains when you unpack it, it contains 2 mathematical notebooks and then one text file and 2 directories which are empty. Okay, so far. So today we want to work. We're going to use this this test.m notebook. So I'm going to open it. And we're going to start with the first section, which is the warm-up exercise. Okay, so let's open it. Can you read? Do you want me to enlarge a little bit, perhaps? Better, okay. So the idea is to consider the following problem, which, as you will see, will be a standard problem in what we will do. You should not care how you came up with this problem. For now, let's just try to solve this problem. And the problem is, consider a vector made of 2 entries, this AB vector, and you want to maximize this combination, the scalar product, AB dot 0 minus 1, which is actually minus B. So you want to maximize over the entries of the vector A and B, such that a bunch of constraints are imposed. One is just a normalization condition. Basically, I'm imposing that this vector contracted with 1, 0 has to be 1. Okay, so I'm basically fixing one of the coordinates to be 1. And the other condition, it's somewhat less intuitive, is a condition on it's a polynomial in X, which contains A and B as parameters. And I would like this combination to be positive for any values of X larger than 0. Okay, so this problem is very simple. But suppose that you are some elementary guy which doesn't know how to take derivatives. So let's try to address this problem in a different way. Of course, before doing that, let me show you that this problem has a very simple solution. Okay, this substar should be B star, of course. Okay, so the solution, this object here is minimized whenever B has some value, B star, which is exactly this. Okay, it's very simple. You can just simply take the first derivative with respect to X and minimize. And then because this is the minimum, so this is the minimum of this polynomial, or this function, you want this minimum to be above 0. And so if you try to solve this condition, that the minimum is below 0, you find values of x. And then you plug back x inside this B star solution, and you find that, sorry, let me try to open this with mathematics. I don't know why it has converted it in this weird format. Anyway, I think you should be able to understand. If somebody is not familiar with Mathematica, please raise your hand. Okay. Here I'm not doing anything. I'm just so this B star should just be B. Okay, B star. I don't know why he's not writing in the natural way. Okay, so so you can find the solution exactly of this problem. Okay, and the B that optimizes this scalar product and obeys all these constraints, you can obtain exactly and has this nice form. Okay, it's some number. But now let's try to address this question in a more numerical way. Okay, this is a very complicated question. Well, in a sense, this is sort of complicated condition. You have a polynomial in X, and you want to minimize it. It has to be, sorry, this one. It has to be larger than 0 for all values of X. Okay, so one idea could be to discretize this constraint for different values of X, and try to impose this condition for in a certain range. And this is a zero-step approximation. So what I'm going to do here is I will discretize, I will choose a range, which will be just a table of values of X in a certain range. Okay. So this range here, you can look at what it is. It's just a bunch of values of X. Okay. And then I will consider the discretized version of the constraint. So we'll evaluate the function. This is the function that has to be positive for any x, and I will evaluate the function for x belonging to the range. Okay? So this gives me a set of constraints, a discretized set of constraints. And now, instead of imposing, can you read? Okay. Instead of imposing that the condition has to be valid for any x, I will just impose that the condition has to be valid for specific values of x. Okay? And so this problem here is called a linear programming algorithm. Okay? It's a linear programming problem, if you want. So it's telling what I'm trying to solve is a bunch of linear conditions on A and B that involves A and B, and I have a lot of them, right? Constraint here has a lot of, it's a vector with many entries, more than 2,000 entries. Okay, so I have many equations, and I want each equation which is linear equation in A and B to be positive, and I also want to maximize the scalar product AB contracted with obj, and I also want to impose the condition that AB contracted with norm has to be 1. Okay. So perhaps I can draw a picture of the problem that I'm trying to solve. Okay. Yeah. You want to put it in front, or because of the? Okay. So let me draw a picture of the space AB. Okay, let's say this is A and this is B. And I have a lot of linear equations of the form coefficient 1, A, plus coefficient 2, B, larger than or equal to 0. So this is just a line in this space. So I have a line here, then I have a different one, line there, a line there, okay? And each line identifies a half space. Okay? And each of them. So there, and also this one. Okay, so the region which obeys all the constraint is going to be the intersection of all these lines. In particular, something like this. Yeah, it's going to be a convex region. And inside this convex region, you have, so first of all, you would like to establish if this region is non-empty, which is not a trivial statement if you have 2,000 equations. Okay, it's not a trivial statement to address. And also, you would like to minimize a scalar product AB dot 0 minus. So there are two questions. One, establish that is non-empty. I would like to move inside this region and find, so this condition here defines a gradient in this region, some direction, and I want to find the point which is extremize this gradient. Okay, and the solution is always, this problem has always a solution because it's a linear problem. Okay, so this problem here is called a linear programming problem. And nicely enough, Mathematica has a function to do that. Is the problem clear and the geometrical picture clear? So the function that I'm using is called linear programming, not surprisingly, and it takes 3 entries. One, obj, is the vector that you want to minimize. So this function here finds a vector x, which is, in our notation, is going to be AB. Okay, and this vector x has to minimize the scalar product with obj, and it will be subject to the constraint x constructed with some matrix larger than larger than this vector b, and also x larger than 0. And also I will impose that, sorry, this should be norm. I will impose that this normalization condition, otherwise the problem is just unbounded. Okay? So norm of x has to be 1, which in particular, so since norm is 1, 0, I'm just, as before, I'm fixing the coefficient a to be 1. And so you can just run this. This problem is the mathematical implementation of the problem that I was trying to solve. Okay? There's a bunch of linear equations that defines a region, a convex region, and a gradient inside this region that has to be extremized. So if you try to solve this, nicely enough, you get a solution which is 1 as requested, because the coefficient a has to be 1, and then the coefficient b here is 1.8427, and if you compare with the exact solution, so here there's a minus. I should be clear. I should clarify. If you look here, I inserted the minus because linear programming it doesn't minimize, it maximizes things. So you have to revert. So I basically change b into minus b, but it's the same. And the value that I found is literally is the good one. So here now I can check a fortiori that the solution that I found is a correct one. So what I can do, I can take the function, plug in the result for b that I obtained, and plot. If you do that, you get a nice function which is always positive. Which is good because you requested that this function here had to be positive for all x's. Okay, now you can do a slightly more more precise check, because here in this minimum it looks like it's going negative. So if you check if you make a plot, a zoom in of this region, you get that the condition is actually violated. And the reason is that we discretized the problem. Okay, we imposed positivity only at a given at a discrete set of points, and these points are the blue ones. But the line is always positive when in correspondence of the point, but it goes negative in the between simply because we didn't impose positivity in the middle. So everything seems to be very consistent so far. Okay, I would like to ask if there are questions about what we are doing here. Yes? No question? No question. Is the problem that we are trying to study clear? Sort of? Okay. Is the approach that we use clear? Okay. So this was one approach, but as you have seen, it has the one downside, that we are not really imposing positivity for all values of x. Okay, we discretized the values of x, and we only imposed a finite number of constraints, and so it can be that. So the result is pretty precise, but still the constraint is not exactly fulfilled. So one alternative is not to discretize. Okay, but if we don't discretize, then we have a problem. Well, the problem that we are trying to solve is more complicated, because we really want to impose positivity for all values of x, and this is a polynomial. Okay, so the SDPB is a software that actually addresses precisely this question. Okay, given a polynomial, which is a combination, let's say, given a polynomial which is a combination of two polynomials with different coefficients, a, b, okay, it looks for a solution AB such that this combination is always positive for any values of x. Okay, this problem is more complicated than the one before, so I cannot explain in a very simple form, like in a geometrical form like that one. But still, it's a problem that has been studied in many ways in the literature of convex optimization. So there is an algorithm which is called semi-definite programming algorithm, which precisely addresses this question. Okay, if you have a combination of polynomials and you require these polynomials to be positive for all values of x larger than 0, there is a well-defined algorithm that addresses this. And so this algorithm has been coded for you in a C++ fashion, so you don't have to get your hand dirty with that. And you can install it if you manage to. And this is really the SDPB. Okay. So what I would like to do now is to show you how you can use that package to study the very same example that we did now, and obtain the very same result. So the first thing to do is to load this Mathematica package, which is called sdpb.m, which contains a bunch of functions, which you don't really need to know what they are. Okay, it's a bit complicated Mathematica package. You don't really need to go through this. Okay, it's been written for you. So let's load it. Okay, and then what is important is this function here. This function defines how you call this package. In order to do that, we have to write a text file that will be then fed to SDPB. So the function that writes the file is this write bootstrap SDPB, which is contained in the SDPB.m file. So this is for you can be a black box. You don't need to know what it is. Okay, it's just a black box. It takes whatever you define here and it converts it to an XML file. The important point are the input. Okay. Again, we have three inputs. One input is the vector that we want to minimize, which in our case is 0, -1. If you look at our problem, then there is the normalization vector, again, as before, 1, 0. So this fixes, basically fixes one of the two coefficients to be 1. And then there is this more mysterious one, which is, so this is, generically this can be a list of stuff. Okay, this is, in this case, is just a list of with a single entry. And in this list, what I'm doing, I'm giving to SDPB the polynomials that has to be combined. Okay, so it has this very peculiar form. You have this positive metric with prefactor, which is just a wrapper. Okay, it doesn't do anything. This is a function that wrap things. It doesn't do anything. It's just a container. This container has two entries. One is it has to have this form. Don't ask me why. It has to have this form. Is basically is the prefactor of the polynomial that doesn't depend on the coordinate. Okay, it's just the prefactor here, and it has to be positive, but it can be whatever you want. You can even put 1 if you don't like this. Okay, this is chosen to have some nice convergence properties, but you don't need to know that. And here inside, I'm passing a list of polynomials. Each entry is associated with either A or B. Okay, so the first entry here is the first one. The second entry here is the second one. Okay, and what this package will do will take combination of this polynomial and look for a solution that makes them always positive, and also will maximize A and B according to our request. Okay, so notice that generically here you can pass a matrix. Okay, so this is the second entry here has a lot of parentheses. Oh. Okay, so generically it can be more complicated than this. Okay, it can be, we'll see another example, it can be so these two can be, if you want, this is a 1-by-1 matrix. It can be a 2-by-2 n-by-n matrix, and each element of the matrix has to be a vector. So generically you can have something like vector 1, vector 2, vector, it has to be symmetric at least. Okay, you can have something like this, and each element, it's a vector. But in this case, it's just a 1-by-1 matrix. Very simple. Okay. So once we have defined all these once we have defined the list of polynomials, the normalization, and the quantity that we want to maximize, we can just call this function, which take as entry the name of the file that we want to write, and then this combination of stuff. Okay, so I initialize it, and then I can call it. Okay, and I call it with some name. So this is a name that I choose. This is the file that will be written by this function. So if I do it, it basically takes nothing. But what it has done, it has written test.xml inside my folder input there. Okay, and if you try to open this, there's a bunch of numbers. Okay, this is a format that has been chosen to be fed to be given to SDPB, but basically a list of coefficient translated in the appropriate form. Okay, now if you manage to install SDPB, this will be in some folder for you. So you have to find this folder in your computer. Okay? So normally it will be the same for all Mac users. It will be the same. I'm not sure. Somebody else can have a different folder. You have to find your folder where this executable SDPB is. Okay. Once you have found it, you can define your SDPB directory in this way. And for instance, we can do two things. We can check that we have installed SDPB correctly by running this string here. Okay, this is a command. Okay, this is a command. It calls the executable with this option ---- help. What it will do, it will just print out the help function, and I'm redirecting the output of this command into this file, which is my. So if I call it run, I run this command in the front line. Okay, I do it. Where is it? Sorry. Okay. If I do it, I have created this file here. So this is the output of SDPB when I call it with the ---- help option. It just tests that everything has been installed correctly. So you should try this option. But now let's do the actual computation. Oops, sorry. So now I have to call the package. And the way to do it is to call the package with -s option, the name of the XML file that we generated, then -p is basically a file which contains all the parameters that has been already defined. And again, I'm redirecting the output of everything inside some output file. So the actual computation, I will run this command that I define with test.xml as an input file and test.out2 as output file, which I will put in my output directory. So if I run it, now, sorry, if I close again, where is it? Sorry. Okay. So if I do it, I generated inside the output directory this test.output2, and if you open it, you will see that a lot of stuff had happened. So okay, here you have a bunch of you have a summary of your input file, the output file, and everything. These are the parameters that were already contained in this param_dir. Okay, and a lot of stuff has happened. Okay. This is, each line corresponds to an intermediate step of the algorithm that you don't need to know because I don't have time to explain. The nice thing is that in the end, he found a solution, and the solution is literally the one. So the solution can be read here in the primal or dual objective, these two quantities, which are basically the value of the parameter that you maximized. Okay. And they nicely agree with they nicely agree with the exact solution that we obtain. And now if you try to plot the function, so I didn't do this, but if you try to plot the function with this new value of b, you will see that it's always positive. There are no negative regions now. Okay, so here I also have another example just to see how to, well, this is another definition, would be another definition of this test function with a more complicated problem, but we don't need to go through this. Instead, I would like to see if there are questions. Did anybody manage to run the code? It works? Okay. Anybody else? Okay, that's good. So, of course, it's a bit obscure right now because you don't know, first of all, why we are interested in this kind of problems. Why do we have to optimize something over a set of constraints? This will become clear tomorrow, for instance, because the consistency condition of a conformal field theory can actually be recasted exactly in a problem of this form. And generically, you don't even want to maximize or minimize things. You just want to know if it exists a region that satisfies all the constraints. Okay? In that picture, generically, in the problem that we want to address, you don't need to maximize a gradient. You just want to know if this intersection of all possible constraints is empty or not. That's the kind of problem that we will deal with. Okay, this SDPB is a software that has been developed to efficiently address this question. Okay, so far it's just a shady software that solves some not very interesting problem, but as you will see in 2 days, this software can be used to actually get interesting physical prediction. Any question about the usage of this? Okay, then if there are no questions, I think I'll let you play with this notebook. If you have questions, you can of course come to me. If you don't understand why the input has to be like this, you can go. So there is on the web page that was linked to download the package. There is a manual which explains what a semi-definite programming is, what is the mathematical interface, and there is this example that I also rearrange a little bit. And of course, there is a whole theory behind this that you are encouraged to explore once the motivation to use this will become clear. Okay. Okay. I think I'll stop here for today. And tomorrow we're not gonna use SDPB, so we're gonna use it in 2 days. So you have time to install it if you want and play with it. Tomorrow we're gonna just use Mathematica for a totally different reason. Okay.